right? So we got a discrete probability distribution. Now let's go back to just the overview. Don't pretend it's binomial or anything else. Let's just look at it from an xp of x standpoint. From an xp of x standpoint. What's the minimum IQ score you could get? Theoretically, I guess.
0.
I guess you could have an IQ of 0 if you have no mental age. 0. What's the next IQ you could have?
Oh, it'd have to be at least 1.
Would it? I'm not thinking it has to be. Because go with me. I'm 40, right? If I test at an IQ of mental age 1, my IQ is therefore 1 over 40, which is less than 1. You see what I'm getting at? It's actually less than 1/100. Well, it's around 1/100-ish. It's 1/40th. So my question, this is a bit nitpicky, Marty. For a discrete distribution, Marty is correct. This would have to be 1, then this would have to be 2, and this would have to be 3, and you just keep on going until you got to what? Actually, you could have an IQ above 100. You'd keep on going. I'm gonna, if you don't mind, I'm gonna put n in here. Because I'm gonna try to keep this more general than specific. Generally speaking, you have to keep going until the biggest possible value you can have. Compared to the chickens, right? The minimum number of girls you can get is 0. The maximum number is however many Max picks out of the bin and puts in a little box. And then you have all these probabilities that go with them. And you know for a fact that if you calculate all these probabilities, they sum up to 100%. Very, very nice. And we have gotten very, very comfortable with that. And I think it's fantastic. I don't think we should get uncomfortable with that, because that is awesome when you have discrete data. And that's where it falls apart. That's where this falls apart. This falls apart because how many numbers are between 0 and 1? Say that again, Jolene. Infinitely many. In a discrete world, there are none between 0 and 1. You cannot purchase 0.23 of a chick. You can get 0, you can get 1, you can get 2. Those are counted. But if you're measuring, and Marty, this is what I was trying unsuccessfully to explain to you. Your question was great. I can have fractional IQs. Most people do have fractional IQs. Because think about the measurement. I just gave you the answer. Your chronological age under your mental age. Age is a measure of time. Time is continuous. So you can't fit time into a finitely numbered list like this. So while this is fantastic with the idea of a discrete distribution, it falls kind of flat when we have to deal with continuous distributions. It falls flat when we have to deal with continuous distributions. Yeah. What do you do with continuous distributions? We need a whole new approach. Mathematicians dealt with this hundreds of years ago, maybe thousands of years ago, I'm not even sure. What was one of the first things you guys learned about in algebra class? One of the very, very first things you guys learned about in algebra class. Do you remember? Think back to all the topics you learned about in algebra. Anything. X, before X, even before X. Guy, go ahead.
Using a letter.
Oh, before variables even. Thank you. Yes, variables was huge. We're going to keep using that. Obviously, we're using it right now.
What do you mean, like the associative property?
Before that even. Go back before that. What did the associative property apply to? Say again. Addition of what? Numbers. What kind of numbers?
Whole numbers.
Only whole numbers?
No, all numbers.
Real numbers. Oh, wait a minute now. Real. What the hell is a real number? Give me an example of a real number. Throw them out.
1.
1, 2. Think outside the box.
0.5.
0.5. Think outside the box. More.
2/3.
2. More. Keep going.
0.002.
100. I'm just getting happy. Keep going. How about square root of?
7.
That's too easy. That's 8. Square root of 7. That's ugly, isn't it? Square root of 7. Square root of 7.23. Even uglier. All these numbers. If I had to plot all these numbers on the board, I'd have a hell of a time, wouldn't I? So what did we invent to do it? Before calculators, they didn't have those 1,000 years ago, Cassidy.
Abacus.
That was discrete. That was for counting. Abacus was just a quick way of counting. Good. What did we invent? You guys started drawing it, you were probably teeny tiny when you drew it. So you guys just said all those numbers, right? So you said, I heard 1, I heard 2. Root 7 is what? That's a little bit below 3, right? That's like over here. 3's over here, so root 7's like there.
Number line?
Yep. Say it again, Di.
Number line?
We invented the number line! We said, this is going to be ridiculous, because if I have to draw all the numbers between 1 and 2, Jolene already said there are infinitely many. So 1.5 is in there, right? And then 1.25 is in there. And 1.125 is in there. But so is 1.16 and 1 3/16. And if you keep putting all these little dots on the board, eventually what are you going to have?
A line.
You're going to have the line. So we said, to hell with the dots. Let's just draw a line like this. Let's just draw a line like this. That line with the arrows indicates we've got all the numbers, a place for all those numbers, without actually having to list every single one of them. This was a huge step in mathematics, but just so you know, it's something we take for granted.
Yeah.
We do, right? We take it for granted. But it was a humongous step in mathematics to do that. It was a humongous step. So now, why do we like this right now with our topic here?
Because it's showing you the continuous.
Because we get all of our data. Yes, yes. Now, I want to talk about, we're going to talk only about the normal distribution today. Only about the normal distribution today. And when I say normal, I mean bell-shaped. And we're pretty much only going to talk about this the rest of our class. So when I say today, I mean for the next 8 hours that we are together. 7 hours. 6.5 hours we are together. Yeah, ish. Somewhere. 6.5 hours. Sad. It's not much time. It's plenty of time. We're plenty of time.
Let's add 10 minutes.
Say that again.
Let's add 10 minutes.
Let's add 10 minutes. Let's add 10 minutes 3 times. Now, I don't think you can see it on that screen. Let me see if you can. Hang on that first distribution. You can! Oh, you can't see it at all. Hang on. So, you may have noticed, you probably didn't, that's okay. On this, I'm sorry, I said I was going to bring it back up again. Yes, here I am. There's the normal distribution kind of at the center of everything. It's gorgeous. It's absolutely gorgeous. This guy over here is called the standard normal. I gave you guys a program last week along with binomial called STANormal. STANormal does this for you, and you're about to see what it is. When I say does it for you, you'll see momentarily. We'll get to it in about half an hour, maybe even less. There's a conversion factor between the standard normal and the general normal. And the best non-mathematical way I can describe this to people is, if I give you the normal, I give you a fish. If I give you STANormal, standard normal, I teach you how to fish. Does that make sense? Okay? This is showing you the process via which you can get to this one. But if I go straight to this one, it only works for one case at a time. So this will work for all cases. That might not make any sense right now, but non-mathematically, think of it this way. You're learning how to fish versus I'm giving you a fish. That'll make more sense in 20 minutes-ish, somewhere in there. Okay? So let's I think I can explain numerically a little better right here. The standard normal horizontal axis has the number 0 in the middle of it. Now when I say middle, I'm talking about a non-mathematical middle. You can't technically have the middle of a number line, can you? I mean, theoretically speaking, it goes on forever, infinity left, infinity right. Which, by the way, the damn kindergarten kids figured out the number infinity. I want infinity plus 1. I'm like, well, technically, kid, you can't add 1 to infinity. Shut up! Okay. Okay. And you can, but that doesn't get it. They don't get that. But so I'm going to put 0 in the quote-unquote middle of the number line. Then you have 1, and 2, and 3, and so forth, and -1, and -2, and -3. And these numbers have numbers in between them, obviously, numbers in between them. What I want to talk about with the standard normal is, since I'm putting 0 in the middle, 0 is going to be the average of the standard normal distribution. I'm telling you that right now. This is a little backwards though, isn't it? Usually we have to have the distribution first to find the average. Usually we have to have the distribution first to find the average. Don't worry about that. That'll make sense within 10 minutes. The standard deviation of this one is 1. Just like it has been all along, as far as 1 standard deviation, 2 standard deviations, 3 standard deviations. Same basic logic. We'll come back to that momentarily as well. Come back to that momentarily as well.
And this
Now,
is just for a standard?
This is for the standard normal. Thank you for the segue, Peg. That was perfect.
Standard,
You can-
normal, continuous?
Yes, this is all the bell curve.
Right.
It's the standard bell curve, the standard, quote unquote standard. I know it doesn't make a whole lot of sense. I'm kind of giving you the pieces of the car. It's like the Johnny Cash song. The pieces of the car. The car will run, but I'm showing you a piece at a time right now. Now, I want to give a hint to later. I'm going to put this in green. Write it down if you want to right now. Don't write it down if you don't want to. You can also have the general normal. Now, the general normal is going to vary depending on what you're talking about. Are you talking about IQs? Are you talking about LDL levels? Are you talking about heights of American women? Are you talking about sizes of those BBs? Are you talking about the volume of that gas tank? Right? Let's pick one. Let's pick the IQs for a second, right? What was the average IQ?
100.
100. That means 100 would go here, right? That means 100 would go there. Instead of 0, you'd put 100 there. What was the standard deviation? Do you remember? It was 15, yeah? So what number would go under 1?
115.
115. 15 above, yeah? How about at 2?
130.
How about at 3?
145.
Everybody buying that? Each standard deviation you go up picks up 15 more. What would go here? 85, 15 down.
It's all normal.
Dull normal. Exactly. There's your dull normal. 90 to 80. That's dull normal, right? Good. Then 70 down 2 standard deviations, and then what, 55? Here's your idiots. Or your imbeciles, whatever, I forget.
So it would be sharp normal if you're a...
Oh, wait, bright normal. I Googled it. It's
Right.
bright normal. Used to be called gifted. I think gifted's off now. What the hell's gifted called? Well, genius is also gone. Genius used to be an IQ score.
130 above or something.
But it's gone. They don't call it a genius anymore. They call it something else. Well, 130, you can see why.
Two
What?
Two
Here's a
standard
qu-
deviations.
Here's a question for you. What percentage of people would be geniuses, i.e. IQs above 130? More than 95. It's slightly more than 95. You guys are making good connections, though. From here to here is what percentage?
95.
That's 95%, right? So the ones that are above here are also above the ones that are down here. So let's logically think through that. Let's think through that logically, right?
2.5%.
So 97.5?
97.5% would be below that, wouldn't they? 95% would be here to here. So if you know that, you also know 5% is here and here. No, here and here, yeah?
Yeah.
So that means this has to be 2.5 of that 5%.
Right.
This 2.5 plus this 95% is 97.5%.
So-
Which means if you have an IQ of 130, you're better than 97.5%. You're in the 97.5th percentile for IQ score. Pat, go ahead.
I was going to say, or the top 2.5%.
Or the top 2.5%. So what you guys are doing very effectively, by the way, is you're coming up with this. Now, what the hell is that? What did I just draw off the bell curve? Yes. But what does it stand for?
The IQ distribution?
Of what? So essentially, look at this chart right here, x and p of x, yes? What does this correspond to in this chart? The x's, yeah? These are like the x's in this chart. Now just FYI, this will make more sense as we go. The standard normal, and I don't know why this letter is used. I don't know why, I don't have a good explanation for you. These are generally called z-scores. When they're on the standard normal distribution, they're called z-scores. I don't know why. I don't have a good historical answer for you on that one. When they're not on the standard normal curve, they're called x-scores or raw scores. We'll come into those more on Thursday. But when they're on the standard normal curve, they're called z-scores. I do not know why. I wish I did. I don't. So, but what you guys just said is correct. These numbers correspond to the left column of the discrete. So what corresponds to the right column of the
The
discrete?
probability that the X score will occur.
the probability that that given score will occur. The height of the curve corresponds to the probability of that particular numerical value. And you can see now why the curve is the best way to do this. You can see now. You guys already know. You already solved a question for me. I'm going to take the IQs away if that's okay with you guys. I want to come back to those, but I think they might be confusing things right now. Let's take these away. For now, we'll put them back. Maybe by the end of class, we'll see. You guys already know certain problems and their solutions based on this curve. So, I'm going to slide over this way a smidge, back out a tiny bit. Okay, so you know that the percent of the curve between z equals -2 and z equals +2. You know the answer to that. What percentage of the curve is between -2 and 2?
95.
You know that's 95%. We've been talking that for 6 weeks now. Nobody's ever stopped to ask, why is it 95%? We'll come back to that. We'll come back to that. We know that that's 95%. Now, in order to know that, what we have to do is, mathematically, we have to grab a marker. Let's use a good color. Let's use green. And we have to say, okay, that means I have to find the percentage of the time I see -2, which is given by that value right there. I'm not going to tell you what that value is because it's irrelevant. I have to know what -1s is right there, yes? I have to know what zeros is. That's the average, right? So it's the most likely. Anybody know what that percentage is? Guesses?
Which one?
The percentage of zero, the highest, the highest. What percentage, what probability would be associated with just zero itself? Guesses? Any guesses? I kind of intentionally didn't give you an axis over here. So 50%, that's damn close. It's closer to 40%, believe it or not. It's closer to 40, but don't memorize that. Don't memorize that, and you'll see why momentarily. Linda, you'll see why momentarily. We'd also have to know what the chance of 1 is. We have to know what the chance of 2 is. But what other numbers would we have to know the chance of? Give me another one in that range between -2 and 2. 0.5. What else?
Square root of 7.
Square root of 7. Actually, that's over here. How about square root of 3?
Okay.
Square root of 3? Negative square root of 3? That'd be down here, right? What else? Throw another number in.
All the lines in between.
1.1? Say it again.
All the lines in between the lines.
Basically, every value between -2 and 2 has to have a vertical line drawn up. And we have to calculate that, right? And when you do that, you end up shading the entire curve between -2 and 2. How much of the curve did I just shade?
95%.
I just shaved 95%. It's the same thing, Monica, you did on the IQ curve earlier. When you looked and you said, yeah, if I cut here and here, I get the fences. Yeah? You've done other fences, haven't you? Haven't you also done the fences within 1 standard deviation? You have? You have? Between 1 and -1? What percent was that? Do you remember? That was roughly your 2/3, yes? So you also know, this is holdover data from before. So the percentage of the curve between z equals -1 and z equals +1, that's 2/3, yeah, that's 2/3. Let's put 2/3, not 95, not 2/3 percent, that's the wrong answer. Hey, I never asked this before. What percent of the curve is between z equals -1 and z equals 0? Don't call this one out. Think about this. Think about this. And I want to hear how you reasoned this one. Don't call it. I want everybody to think about this. Between -1 and 0, I'll color that. Run out of colors. I'll color it purple.
Stay in the lines.
I am.
Isn't that the standard deviation or so?
Yes, those are standard
The
deviations.
thing that you showed.
Yes. So it's we've been talking about it. I was setting the stage for this the entire course, essentially, by calling it 1 standard deviation, 2 standard deviations, 3 standard deviations. That's why. That's exactly why. So within 1 standard deviation on this curve is from -1 to 1. So that's why I had you guys using those numbers back in the day. That's why I pushed pause on your textbook's presentation. I went, that's too early. Not yet. Now, good. Haley!
Can you put -1?
I can put -1.
Thanks.
That's bothering you, isn't it?
Yeah.
Do what I say, not what I write! Carly!
Oh, do you want to?
I want the answer!
1/3.
Why do you know it's 1/3?
Because 2 standard deviations is 2/3, so 1 would be 1/3.
Yeah, so if this whole range is 2/3, what's just this part of it? And what is half of the 2/3, which is 1/3? What assumption is Carly making correctly?
That is an accurate bell curve.
Good, well, good, and always doubt my drawing. That's why I gave you a program, it'll draw it better. But yes, a bell curve is perfectly symmetric over 0, which means any area on this side is beautifully, perfectly mirrored over on this side. So this most definitely is exactly 1/3 of the data, roughly 33%-ish, somewhere in there. Pat, go!
Now, you said perfect bell curve. Now, if you go back to, like, say, the women's height.
Oh, good, good,
Was
yes.
there a gap there? Can you still use this? Like you said.
You can with a margin of error, which we're getting to. You have to put a margin of error on a sample, and we're getting to that.
Crazy.
First things first. This is the screwdriver. Then we're going to see what we can build with the screwdriver next week. Does that make sense?
Yep.
Yeah. You hear what Pat said? I said in a perfect bell curve, you get 1/3 of the data right here, and he said, wait a minute, time out. The women's heights, the IQs, the HDL levels, whatever, or the LDL levels, those weren't perfect. Hell no, they weren't. They were samples drawn from a perfect population. What do you do then? You slap a margin of error on your sample. That's what next week's all about. And that's what 244 is about in spades for the most part. Good question. Looking forward to our last 4 hours together. Tear. Now here's the problem with this. I don't want to have you guys drawing this every single time. You have answered certain questions though. For example, you know now what percent of the population has IQs between 85 and 100. You know, it's 1/3. 1/3 of the population has IQs between 85 and 100. If I was to put that green scale back on that I've since taken off. But the problem with, Veronica, go.
Is that Q2 in there? Am I correct?
Where is, Q2 is here. Because Q2 is the what? Oh, thank you, Veronica. Let's go with that, shall we?
Okay.
That's definitely Q2, because Q2 is the median. So the median is clearly the same place the average is on this curve. Thank you for this awesome question. Where is Q1?
Negative.
Does anybody remember the answer to this? I made you answer it on a quiz like 3 weeks ago, so I'm guessing the answer was no. So let's reason through it. Let's reason through it. What percentage is from 0 down to infinity?
50.
Half of the curve, yes? I say down to infinity. A lot of times it does pinch off. Mathematically speaking, this curve never pinches off, mathematically. But realistically, there's usually a bottom end somewhere to it. So 50% of the curve is that way, 50% of the curve is that way, so the 50th percentile is definitely 0. Q1 is which percentile?
0 to
It's the 25th percentile. It's the low point to the 25th percentile. You guys just figured out that this is what? How much percent is in here? Roughly 1/3, so 33%-ish. That means how much of a percent is from here down to infinity? Careful.
33.
17%, right? Careful. This was 1/3 of the whole curve. 1/3, that would be 1/6, if you will, of this piece, if that makes sense. Does that kind of make sense? Think about it this way. This is roughly 33% of the curve. That means this over here is also 33% of the curve. These two halves are both 33%, roughly 1/3, right? So that's 66%. That means the other 1/3 has to be split amongst these two tails. So, exactly. So if this is 33%, do you agree that this has to be, I'm looking to be consistent. Oh God. Consistently awful. This whole curve here, all the way down to infinity, has to be about 17%. 17% to add to 50?
right.
Is that believable? So tell me, Veronica, this is a great question. Where is Q1? Give me a ballpark of where it has to be. Is it over here? It can't be, can it? It's got to be to this side of -1, yeah? Because if this is 33 and this 17 is not enough. -1 is the 17th percentile, correct?
Yeah.
-1 is the 17th percentile. So the 25th percentile is got to be about here. And as it turns out, that's right around -2/3. That's the z-score. That's the cutoff. 2/3 of a standard deviation. is roughly your Q1. We'll use technology in a second to show you why. I promise, we're getting to that, we'll get to it today.
Okay, but we're going out of 100, so 33,
Uh-huh.
33, and 17.
That's out of 50. The other Q3 would be on this side at positive 2/3. So in other words, your middle 50% of your data, remember in a box plot, your middle 50% of your data is between Q1 and Q3? Yeah, so it is here too. Your middle 50% is between Q1 and Q3, which is within 2/3 of a standard deviation of the average. That means there's a whole bunch of data right here, half. 25%'s over here, and 25%'s over there. It's a friggin' awesome question, Veronica, thank you. Everybody follow that logic? Ish.
Yeah.
Tell me if you didn't, tell me if you want to explain it a different way. No,
Wouldn't it always be like that?
It has to be. By definition of the bell curve, it has to be that way, yes. So now, what IQ scores do the middle 50% of adults have? You know this.
Not between 90 and 110.
Between 90 and 110. Think about why. If the standard deviation on IQ scores is 15 points, 2/3 of that 15 is 10. 2/3 of 15 is 10. So you knock it down 10, you knock it up 10. 50% of people are between 90 and 110. That's looking forward to a Thursday type question, but it was a good question to tie into this right now. That means 25% of adults have IQs below 90, and that means 25% have IQs above 110. We still haven't answered our dull normal question yet, because that was what's between 80 and 90, right? What's between 80 and 90. We've answered partially that. We know it's less than 25%. I don't know how much less yet. Right, thank you. It's a great can of worms to open
Well,
up.
I wanted to see how
Well,
it.
good for you! Now, I have a better tool though. Technology is a better tool. Here's the problem. This is beautiful. I mean, drawing areas, how many of you guys remember doing this in geometry class? Finding the area rectangles and the area triangles, you sketched areas, you would overlay things and remove areas sometimes. Every area formula you have ever calculated is based on something called a Riemann sum from calculus. Carl, you've had calc, right? Yeah. You've done this before. What you do is, essentially, is you add up little tiny rectangles. Because you know what the formula for the area of a rectangle is. Length times width. So what you do is, instead of doing these pencil scribbles like I just did, you actually draw little rectangles. And you add up the areas of those rectangles. And now, of course, that won't be perfect. That's kind of like painting a room with a paintbrush that's this wide, and the room has diagonal walls. You're like, well, I can kind of... So what you do is you make the brush narrower, and you make the rectangles skinnier. And eventually, you let the rectangle shrink down to infinitely skinny, which doesn't make a whole lot of sense because you can't draw infinitely skinny. But what that does is it fills the curve perfectly. That's the mathematics behind when you guys sketch, and the lines are out. But when you sketch that, you're actually doing a Riemann sum, a calculus Riemann sum. I don't expect you guys to do that. Holy crap, that's why I gave you Normal. So we're going to use this Normal program. Grab that bad boy. Grab that bad boy. I'm going to show you how to use it right now. This is going to be our guide through the rest of 243, excuse me. Normal. Now I have to explain, I had to invent a term on it too. I did have to invent a term on Normal that didn't exist. I do want to share with you too